Okay, I switched it on.
Perfect, thank you.
Thank you. Okay, good afternoon, everyone. Good afternoon. Okay. You have a quiz due tomorrow. It's a short one. It was posted sometime back a couple of days ago. I will also be posting a homework that will be posted tonight. It is due on the last day of the semester. Okay, so if you feel like working during the break, go for it. If not, that's also fine. You will be able to complete it after the break is also over. But I just want to post it so that people who want to get started early can perhaps get started early. Okay? All right. And your exam scores will be updated by the end of the day. Please be patient. One of my graders is sick, so my other grader is uploading all the scores. So it'll take a while. But hopefully by the end of the day tonight, you should have all your scores. If you have a problem with your exam grade, you come and talk to me. Okay? All right. So last class we were looking at the RCL circuit. We derived the transfer function and we were also able to obtain the peak. I just want to go through the process a little more slowly. So just a recap. So the transfer function we obtained was the following. The T of S. And here the voltage output was across the capacitor, so VC of S. By the source voltage, this was a harmonic input. So we expect a harmonic output, which is why we are performing frequency response analysis. And the transfer function was the following. LCS square RCS plus 1. Okay. We were able to compare this with the standard form of a second order ordinary differential equation. We were able to extract the natural frequency omega n (1 by root LC). This is particular to this particular system. Okay. And then zeta was also obtained as the following. R by 2 square root of C by L. And we recognized that 2 zeta by omega n, if you combine all these terms together, you end up getting it to be R times C. And so we take all of these and we substitute this into the transfer function. So we write the transfer function as the following. So T of S is 1. This LC times S square, we write it as S square divided by 1 by L times C, okay? And then RC, I just leave it like that. Plus 1, and obviously you see that 1 by LC is nothing but the square of the natural frequency, and so I have the following. T of S is 1 S square by omega n square. Then RC was written as 2 zeta by omega n times S. Plus 1. Notice that the numerator is 1. Okay? And once again, this is particular to the problem we are solving. This is the RLC series circuit. The input is the source input, Vs. The output, importantly, is across the capacitor terminals. If it were across an inductor, the transfer function would be different, and we will look at this. Okay, we will look at this in the next lecture after Thanksgiving break. Okay, then we calculate the frequency response function. Which is T at S is equal to j omega, and then we were able to write it in the following form. This is 1 by 1 minus R square j times 2 zeta R, where R is the frequency ratio, omega by omega n. Okay, so here R and what is omega n? Omega n, just for our own reference, is the natural frequency of the system. What is omega? Omega is the input frequency. The input frequency is also called the carrier frequency. Or it is also called as a frequency that excites the system, so that's an excitation frequency. Okay? So typically in problems I would ask you to calculate the frequency response function, and this is what you will end up getting. Then we decided to say, okay, what's the value of omega, input frequency, that gives me the maximum peak for the magnitude of the frequency response function. So magnitude, T of j omega is the magnitude of the numerator, which is 1. Magnitude of the denominator, please make sure you are squaring the real part, you are squaring the contents of the imaginary part, and you are adding them up together. Okay, it's not j square. So this is 1 minus R square whole square, 2 zeta R whole square. All of this to the power 1 by 2. Okay, square root of that. We did all of this last class. Then to find the peak value, we differentiated it with respect to the frequency ratio R. We found out that the peak occurs is at omega capital R, which is called as a resonant frequency. Omega R is omega n times 1 minus 2 zeta square. Terminology, omega R is a resonant frequency. something that really irks me is when people call this as resonance frequency. There is nothing like that. It is resonant frequency. Okay, please. Alright, and then the peak value itself at omega is equal to omega r. The peak, which is the magnitude at omega is equal to omega r. We simplified this and got the expression 1 by 2 zeta square root 1 minus 2 zeta square. And just for reference, I'm going to write the magnitude T of j omega here. This is 1 minus r square 1. Okay. This is where we stopped. I want to take this forward, then I want to solve an example, okay, very quick, silly example. And then we will go into Bode plots for second order systems, okay, which is slightly more trickier. And I just want to get the record straight, so have you all seen Bode plots for second order systems? In electrical circuits, Bode plots for second order systems, no? Maybe is also fine. I'm going to assume that's a no. Yes, sir. Question. You had a question.
I was going to ask, what is the unit for the TP?
Oh, whatever is the unit for the output. Right. You can figure out the units, right? Because if you look at the unit for TP, this is dimensionless. So this is just a magnitude of the input to the output. So this is essentially magnitude of Vc by Vs max, which is dimensionless, right? Because it's a ratio of two quantities that are the same magnitude. Somebody had a question. Yes.
That equation for T of j omega equals 1 minus r squared 2 zeta r.
Louder, please. Louder.
That equation for T of j omega 1 minus r squared 2 zeta r squared. That thing. Is that going to be general? Like if we get a
No.
differential?
No. That's the thing. So I want to make sure this is specific to our problem. Absolutely, this is specific to our problem, because if you take, and I'll work on this example next class, not today, but if I take the voltage output to be across the inductor terminals, my frequency response function will be different.
Okay. For like the quiz, is there like a general form with like a kind of like a standard form you want the magnitude transfer functions and things to be in? Or
Yeah, for the quiz, your magnitude transfer function will be having a magnitude in the numerator, but the denominator will be the same, for example, like this. And I'm going to get there with the next example that I'm going to solve. You're pretty much laying out what I'm going to teach today. But that's a good thing. Good point. Okay. This is not general. Absolutely not. Depends on where you're getting the output from. If you're taking the output across the inductor terminals, you're going to have numerator dynamics. You're going to have LCS square in the numerator. And then all of that will be the same stuff in the denominator. Okay, so be careful, please. But this works as long as your numerator is a constant. Okay, and I'm going to show you with an example as well. Alright. So before I go there, I want to plot T of j omega magnitude versus the frequency ratio. Okay, so let's do that here. This is R, dimensionless. And the magnitude here is, in this particular situation, does not have any dimensions. Okay, the input and the output have the same dimension, so this is dimensionless, as you can see. So this is T j omega magnitude. Start with R is equal to 0. So first, when R is equal to 0, what happens? You see, when R is equal to 0, focus on this guy. This is the thing that you're plotting. 2 zeta R becomes 0, 0 squared. 1 minus 0 is 1. So my magnitude becomes equal to 1. I start at 1. Okay? Magnitude of T of j omega is equal to 1. And notice, this is regardless of what the damping ratio is. whether the damping ratio is 0, whether the damping ratio is 250, when R is equal to 0, the magnitude is always 1 in this particular case. Okay? And so I start at 1. Let's say this is 1 somewhere. Then let's take the following. Let's say that R is equal to 1. What do I get? When R is equal to 1, and let's say that zeta is equal to 0, let's say that I'm a foolish designer. I say, hey, let's get rid of damping, it's too much to think about. What happens to T of j omega? R is equal to 1, so I have 1 minus 1, 0. And then I have zeta is equal to 0. I have 0 as well there. So that becomes infinite. Okay? Becomes infinitely large. Once again, what am I doing? I'm just substituting values. I'm taking R is equal to 1. So 1 minus 1 is 0. 0 square is 0. Zeta is 0. So this is also 0 square. So 1 by 0 is infinite. So if you design a mechanical system with no damping, and when R is equal to 1, and zeta is equal to 0, what happens to omega R? Omega R becomes equal to the natural frequency of the system. And this behavior is called as resonance. Right? At this particular point, I'm saying, hey, don't put any damping, but then take the input frequency, bring it to the natural frequency of the system. What am I going to get? A disaster in the making. If I am designing a mechanical system. If I'm designing an electrical system, this is great news. For electrical systems, if I'm designing tuning circuits, and if I'm designing, for example, amplifiers and radio station antennas and so on, I want resonance. But of course, I cannot get resonance because I will have a finite magnitude of zeta. So for electrical systems, I need a very high magnitude at the resonant frequency. For mechanical systems, this is a catastrophe. We are mechanical engineers, right? So this is called resonance. And I'm going to write this thing down somewhere here. So at resonance, when zeta is 0, T of j omega is infinite. Okay, so this is really not good for anybody. And that's, let's say, happens there. So this is R is equal to 1. If I plot zeta, T of j omega versus R, for zeta 0, I get the following. Initially, it keeps on increasing. And then after some time, it starts decreasing. But you see, I have this resonant peak that is taking place, and I want to avoid that. Okay? So if you're designing something with 0 damping, you don't want to stay near the resonant region. Then if you start adding damping, let's say zeta is less than, greater than 0 but less than something, you'll see the following curves. I'll explain them in a second. Okay? This is with increasing zeta. Increasing zeta. The first curve is zeta is equal to 0. Then this curve is zeta greater than 0, less than 1 by root 2. We'll figure out why this is the case. And then this curve that I've drawn lastly is zeta greater than 1 by root 2. Okay, so there are 3 curves. This is curve 1. Then curve 2, or 2 is here, and then curve 3, this is curve 2, this is curve 3. Does the figure make sense, or do you want me to redraw it and explain it again? Okay. So first thing is I have the first curve, which is when zeta is 0. Okay, and you can plot it and you can figure out there is something unphysical happening at the resonant frequency. The magnitude becomes infinite, which is why I don't join it. Okay. But then you see that as I start increasing the damping, as I start adding finite amounts of damping, you will see that the peak still occurs. But what you will see is that this peak value will keep shifting to the left. And I'm going to explain that in a second. Okay? And then after some time, if you add zeta and you keep on increasing zeta and it becomes greater than 1 by root 2, you will see that there is no longer a peak taking place. Okay? So those are the three things I want to show. I will be revisiting this figure once again. I'm going to pull the top panel down now. And don't worry, I'm going to revisit this figure again. Okay, so remember, omega r is omega n 1 minus 2 zeta squared. Okay? When zeta is equal to 0, r is equal to 1, this was the first point we made. Let's see what happens when zeta is 1 by root 2. What happens in this case? Omega n (1 minus 2 by root 2 square). Root 2 square is 2, so 2 divided by 2 is mostly 1. 1 minus 1 is 0. Square root of that is 0, so omega r becomes equal to 0. Which means that when zeta is greater than 1 by root 2 or even equal to 1 by root 2, I will not have a peak value at all on my curve. Okay, the peak is no longer defined. Okay, the peak is defined. It's unphysical at this particular value, right? Because when zeta is 0, it is infinite. So nobody wants zeta to be 0, and you cannot have zeta to be 0 because you cannot break the laws of thermodynamics. You also do not want to go, you can go past 1 by root 2, no harm done, but you will not see a peak in your curve. So between these two values is when you have the peak value of the system defined, and beyond this there is no peak. Okay? That is, you can define a resonant frequency only within this range. Omega r is valid only for this particular range. If you go past this range, then there is no meaning for this term resonant frequency, because there is no resonant phenomenon taking place. There is no peak taking place. Okay? So zeta no peak shown or present on the curve. And because of this, I'm going to redraw that curve again and show you. Okay, the first one is zeta is equal to 0. Last one, zeta greater than 1 by root 2. And you can also find out that the peak point of the curve keeps shifting to the left. And that's quite common sense. If zeta keeps increasing, right, between the range from 0 to 1 by root 2, what happens to omega r? Omega r keeps reducing, right? So my peak is going to keep shifting to the left. Okay, so peak shifts to the left for increasing zeta between 0 and 1 by root 2. This is an important curve. Every mechanical engineer should see this in their life at least once and then forget it. Please notice that the phenomenon of resonance is valid only when you are within this particular range, and it's quite obvious to see why you end up with that range, because you can set this equal to 0 and you'll get zeta to be 1 by root 2 as a question.
Will the expression for the resonant frequency be the same even if we weren't looking at the capacitors specifically?
The expression need not be the same depending on the numerator dynamics.
Okay.
So this is for this particular scenario. And this, in some sense, is most representative of many mechanical systems without numerator dynamics.
Okay.
Right, absolutely. So I should make a point, that's a good point to note here. This is for systems without numerator dynamics. What is meant by numerator dynamics is if the numerator itself has some zeros. That's called numerator dynamics. Okay, typically in a system that we are studying here, there are only poles, the roots of the characteristic equation. If the numerator has zeros, that's called numerator dynamics. Not the physical zero, but the definition of the term zeros. Okay? Alright, so that's what I want to talk about here. I want to look at a quick example before we move on. I'm happy to answer other questions. I'll give a brief pause. Questions, of course, related to the lecture. Yes?
If r equals 1 but zeta equals 0 and it shifts to the left as zeta increases, is it possible for r to be greater than 1?
Oh, r can be greater than 1. I mean, this is not when r is equal to 1, you see. So when you look at r is equal to 1, that is when you have, and zeta is equal to 0, that is when you have resonant frequency. Okay, and then as you can see, this is r is equal to 1, but the omega value keeps shifting to the left. So you could still have r is equal to 1, but then the omega values could be shifting to the left. Okay, so maybe I make it a point. So r equal to 1, what does that mean? So r is 1 minus 2 zeta square. So when can r be equal to 1? When zeta is 0. Then what happens when zeta is no longer 0, when r is equal to square root of 1 minus 2 zeta square? You see the value of r as zeta increases. What happens to the value of r? The value of r keeps getting smaller. And that's what I mean by saying that the peak is shifting to the left. Okay, that's a good point. So this is the situation, and this essentially tells you that omega r is omega n 1 minus 2 zeta square. So omega r keeps shifting to the left. This is defined only when zeta is equal to 0. Any other questions on this? Keep it very clear in your mind, this is for this particular system where there are no numerator dynamics. but this is very commonly seen in most mechanical systems without numerator dynamics. When r is equal to 1 and zeta is equal to 0, bad news, and that is the resonant frequency. Okay, but you can still have a physical peak. The magnitude of that peak will keep reducing as you go further, and the location of the peak will keep shifting closer and closer towards r is equal to 0. And all of this happens only within this range of zeta values. Question?
Could you give like a mechanical example of when you would use this plot to like reduce resonance?
Okay. So you could always use this plot when your system model is of this form, which is for a very wide category of system models, right? Because you see, I don't have any f dot terms, I don't have any f double dot terms. If I had those, then there would be zeros in the system, and that will be when you have numerator dynamics, which is my next example actually. I'll be looking at a numerical example, but that's again an excellent point. These are not easy things to digest. If you don't have numerator dynamics, it's this nice spring mass damper model with an external force. Or if I have a torsional body, I have a torsional spring, I have a torsional spring and a damper, torque applied. Okay. Let's take an example, numerical example. And if you want a system model with numerator dynamics, here is another example, since we're talking about it. Maybe I'll be more clear. So, mx double dot, cx dot, kx is equal to f of t. If I take the transfer function, right, so p of s is x of s what's in the numerator? No zeros. Okay, so no zeros. Means no numerator dynamics, and everything that we have studied so far applies to this particular scenario, which is a very broad category of problems. Any problem that you can model is a spring mass damper. Okay? If I have numerator dynamics in a mechanical system, the following example. You've done this in your recitation. Okay? This is a stiffness K, this is a damping element C. This is essentially the model of a suspension of a car, right? The circle represents the wheel base, but the body of the car is so much more heavier than the wheel base, we say that this is massless. But then it is the motion of the wheel that sets the suspension in motion, right? Which means that I'm going to give an input displacement, obtain a response. If I write the system model for this case, I end up getting the following: mx double dot, cx dot, cy dot plus k. Now if I take the transfer function, x of s by y of s is ms square plus cs plus k, and you see that there is stuff going on in the numerator. It's no longer as nice as what we have here. This is numerator dynamics. You have zeros. So this is with numerator dynamics. And in this case, we will have to go through the process of the differentiation once again. You will have to calculate the peak value by differentiating it, write this entire thing in the form of the frequency ratio R, perform the differentiation. I might get a different value for the peak, I might get a different magnitude for the peak. Okay? That will be different from what we have done so far. And so you can see the richness of what we have done so far is, even though very beautiful, it's applicable to a small category of problems. It's not a generalized situation. And you will exactly see the same thing if, for example, I will write this out, but I will not derive it. I'm going to erase this particular panel here. This is not what I plan to do, but it's always good to do unplanned stuff. If I say that my output voltage is across the inductor, then what will happen is my system transfer function will end up being the following. Completely different problem. Just by changing the location of the output. Okay, silly system, RLC, child's play for us. This is no longer child's play. Okay. All right. So that's I guess sufficient with the digression. But happy to answer more questions after lecture. If you want to email me, that's also fantastic. I love questions like these. Okay. Last thoughts. And I want to revisit systems like these which have numerator dynamics, how to draw the Bode diagrams for these. They are not easy. And we will find out a way to make them easy. Okay? Alright, I'm going to pull this down, go for an example, something to help with the quiz. All right, let's take a system. For example, 4x double dot, 8x dot, 20x is equal to f of t. Okay, let's figure out what the peak is, what the resonant frequency is there a resonant frequency, and so on and so forth. Okay, so obtain omega r, P peak. First thing you always have to find out, is this in standard form? What is a standard form, right? So the standard form, x double dot, 2 zeta, omega n x dot, omega n square x is some right hand side, g of t. Okay? It need not be f of t, it could be anything else. So obviously the given system is not in the standard form, as you can see. So you have to put it in the standard form, divide through by the factor of 4. So divide by 4. I obviously took the easier example. So this is x double dot, 2x dot plus 5x is equal to 1 by 4 f of t. Okay? Don't forget that fact. Alright, so now I have the natural frequency and the damping ratio. If I can find it out. So omega n square, if I compare the two equations, is equal to 5. So omega n is the root of 5 radians per second. Okay? And then 2 zeta omega n is 2. Zeta is 1 by root 5. Makes sense to everybody, right? This is standard stuff. Since we are doing frequency response, you have to be a little careful. Different techniques require different finesse, okay? Different types of finesse. So I'm going to take the Laplace transform on both sides of the equation, okay? Or I could either work with this or I could work with that. It does not really matter. So let me work with this guy here. So S square 2s plus 5. But before that, I just want to catch my words one more time. 1 by root 5. You want to check and see, is this within this interval? Obviously the answer is yes. If it is within this interval, then I can define a resonant frequency. So zeta 1 by root 5 is within this interval. And so omega r is actually physically defined. Etc. etc. No numerator dynamics, as you can see, right? No derivatives of f of t present. Then I take Laplace on both sides. 1 by 4 f of s. Or the transfer function of the system. This is x of s, of course, y f of s. Any questions so far? Yes?
Just to make sure you don't need to worry about any input values or about initial conditions.
Oh, no. When you're doing transfer function analysis, you're looking at steady state behavior. So all the initial conditions, they affect only transient behavior. Once again, when you're doing transfer function analysis, and you're going to do this a lot in your control systems class next semester, whenever you're going to take it, you will not worry about initial conditions because you assume the system is stable. And for a stable system, the initial conditions do not affect the steady state behavior. They die off during the transition part itself. Okay? So that's the reason why you don't worry about it. Unstable systems, good luck to you. So I have this system here. This is not the form I want. When I do frequency response analysis, always remember, what do I want to have? I want to have this last term as 1 and everything else divided by that term. Because, recall, for without numerator dynamics, what was our system transfer function? It was T of S is for the RLC circuit S square omega n square 2 zeta. This was our transfer function, and what we are trying to do is, we have done a lot of hard work for this particular creature. Can I apply that idea to what I am doing here? So that I don't need to recreate the whole wheel and the cave person story again. So obviously I start with the transfer function and I bring it to the form that I see there. So I go back to our problem. E of s is 1 by 4. What should I do? I should divide everything by 5. because that's the last creature down there, right? You can see there is 5 there, so this is s square by 5 plus 2 by 5s plus 1 factor of 5 out. Once again, when you're doing frequency response analysis, what do you do when you do second order systems? You have to have this as a factor of 1. And we did this for the first order. Yes, question.
So if we're given a question and it tells us to find the FRF, do we assume, and it doesn't tell us what type of circuit it is, do we assume it's RC or do we assume like RL? Like what would we do in that case?
Oh, so it depends on whether you're looking at a first order circuit or a second order system. If you're doing a first order system, that's what we have done, the RC circuit. Right? So that's going to have a time constant, tau. If you're doing a second order system, it's going to have a damping ratio, it's going to have a natural frequency, and for a certain range of the damping ratio, you will have a resonant frequency. Okay. If it is anything else, what should I do? I should tell you to perform the differentiation again and calculate the resonant frequency and calculate the peak. And since we have done it in class, please expect to be asked that. Okay? That's the reason I'm doing it. Alright, what's that 5th creature there? 5 is omega n square. Right? Because you see up there on the board, omega n is root of 5. So I'm going to have this as, take this creature of 5, it has no business in the denominator, put it in the numerator, so this is 1 by 20. And now this is of the form s square by omega n square. 2 by 5, 2 zeta by omega n is, zeta is 1 by root 5, omega n is root 5, so that's 2 by 5, so this is fantastic news. It's now in the 2 zeta. This is the form that it is present in. Now what's the frequency response function? Just substitute s is equal to j omega. Okay, so the FRF is, don't forget that 1 by 20 creature. There's 1 by 20, 1 minus r square j times 2 zeta r, where r is omega by omega. Yes.
Why did you validate that 2 zeta over omega n equals 2 or 5?
Oh, because, yeah, go on.
Is there any case where it wouldn't just be the number before s?
It should be, but just for my own sanity, I always make those checks, because this tells me, hey, what if my zeta value is wrong? Right? If I had chosen it to be wrong, then actually what if there is no resonant frequency at all? Right. Yes, question.
Is there an extra square on the 1 minus r squared?
Yes, thank you. I'm getting ahead of myself. Thank you. 1 minus r square, and then this is the frequency response function, fantastic. The validation is just done for a sanity check, for checking to see if everything is working out, and of course it should be, right, as we have been doing it together. Magnitude of t of j omega. One by 20. Now we solve these squares to the power 1 by 2, and now if you do your differentiation to find omega r, in this case the numerator will have nothing to do with the magnitude of the resonant frequency, the numerator on the magnitude of the FRF. Okay? You will still get the resonant frequency, you be my guest, do the differentiation and all that. This is the same as what we had before. Makes sense to everybody? So far so good. Start with the given system, reduce it to the standard form, figure out the system parameters, figure out, hey, is zeta between 0 and 1 by root 2? Yes, fantastic. There is a resonant frequency. Because the system has no numerator dynamics, I have a sneaky suspicion it's similar to the RLC circuit with the output across the capacitor terminals. Don't take anything for granted. If you are like me, you would go back and differentiate this to get that result again. In certain problems, I'll tell you, you don't need to do the differentiation. You can just directly go through and find the answers. Okay? In problems where I have you do the differentiation, the numerator will have its own dynamics. And in those problems, you have to do the differentiation, however messy it is. You may end up with a different expression here, completely different one. But thankfully, it is not the case for this problem and for your quiz. So what do? I say, this looks like the RLC problem in lecture. And so what should I say? Omega r is omega n times 1 minus 2 zeta square square root. What should my T peak be? If I were doing it for the RLC system, my T peak would have been 1 by 2 zeta 1 minus 2 zeta square. Okay, if this were the RLC system with only 1 on the numerator, but here I have something else on the numerator, it's 1 by 20. So I take that creature and I put it on there. Does this make sense to everybody? Once again, it looks like the RLC problem. What's the only difference? The only difference is here the numerator is no longer 1, it's 1 by 20. In my RLC problem, RLC series circuit problem, when we did the differentiation and calculated T peak, it was 1 divided by